In this video, let's talk about the potential of converting add to be tail recursive. So what we could do, there's two ways we could do this. One way is to use an explicit third parameter that keeps track of the recurring sum. So in fact, let's write that very quickly. So static int add tr, and we're just going to say tr1 because just for the heck of it. So we're going to return add tr helper 1 in m. So notice that we pass both parameters, and then we're going to start this off. We're going to start the accumulator off at 0. Okay. Now we're going to do private static add tr helper 1. Or well, we need a return type first. Int n, int m, int acc. And now we're just going to copy again our case analysis. Okay, so this has to be add with some stuff. We don't know what it's going to do, but we know that n is going to be trending to 0, so we may as well do sub1 of n. Then m might change somehow, and then acc might change. So in this case, we're going to return acc plus m. So if you watched the previous video, which you should, we noticed that in swap AB we return s. We don't return the empty string. But in the tail recursive method, we have to return the accumulator plus s, because if we get to the base case and we just return the accumulator, then we might be forgetting some things to add on to it. And what do I mean by that? I mean, so let's finish the implementation. So we're going to add 1 to ACC. Let's see, what's wrong? Oh, add tr helper, my bad. So let's go to our tester. We'll just very quickly change this. Add tr1, add tr1, add tr1. So let's see what happens if we don't return ACC. This should return what? Let's see. So for this case, it expects 3, but it returned 0. And why is that? Well, it's because the, let's see, which, yeah, so it's this one. So expected 3, the actual was 0. And the reason why is because actually, oh no, okay, no, okay, yeah, sorry, okay. So yeah, so this is kind of the problem here. So n is 0. For some reason, I didn't realize that n was 0. Because n is 0, we immediately return ACC, which is also 0. Right? So we hit our base case by default because n was 0, and we return ACC, but the problem is that there's some information that's left over. That information that's left over and would be taken care of by the stack unwinding is that plus m. So let's just do ACC plus m, and now all of our tests should pass. Very good. Now, the thing is, and now my cat is right behind me, so, hello. Okay. So, the thing is, this is all great, but there's not really a need to use an explicit accumulator for the add method. And why is that? Because we can just use the value of m as the accumulator. If you think about it, let's write out the trace for this. So let's say we have add of 3 and 4. Why not just have sub1 of n and then add 1 onto m? This does the exact same thing, and n now functions as an accumulator. And then when n is 0, just immediately return m. So there's no stack unwinding, and there's no explicit accumulator. Okay? So what am I trying to show here? I'm trying to show that not all methods need an explicit accumulator. Okay? That's very important. And there's not a whole lot of methods that follow that structure. Most of the time you're going to have an accumulator, but there's one other example where you don't need an explicit accumulator, and that is actually the greatest common divisor algorithm. So if you read the book, you'll understand what that means, but let's rewrite this algorithm to use the what I would argue is the better implementation of tail recursive add. So we'll call this add tr2. And then here, notice that we also don't need a driver method, right? Why don't we need a driver method? Because the caller of add tr2 absolutely needs access to both of these parameters, right? We have to know what n is. We have to know what m is. And because of that, we can't, there's no need to, first of all, we can't privatize this, because if we did, then no one would be able to call it. Second off, there's no accumulators that we need to hide, so there's no need to make a driver method when we don't need to. Okay? So, let's just not do it. So, in the is0 case, we already return m, which is kind of nice. Okay? So we take care of any case where we start off with n being 0, we just immediately return m. But now we can just move that add 1 operation inward. That's it. That's literally all it is. And in fact, sometimes when people first show off recursive addition like this, they show this version of add. But I didn't want to do that because I wanted to exemplify what happens when why we have the stack in the first place, and what happens when we unwind the call stack. Okay, so now let's test this. Let's reformat this. We'll test add tr2. Add tr2. Run. And all tests pass. Okay, so we've written 2 tail recursive versions of the same algorithm, and in general, if you can write a tail recursive version without an explicit accumulator, that's a good idea, but most of the time you're going to have an explicit accumulator, so there's no problem in writing a version that might look like this, for example. Sometimes it's cleaner, sometimes it's not. And in this case, it's actually cleaner to not use an explicit accumulator.